So I want to give you a quick overview of using the trapezoidal rule for integration, the basic concepts behind it. First, we'll start with this idea that what we're looking for is the area under a curve, and we're looking for really kind of an estimate of that area. So starting off with the basics, right? So here's a function. All it is a straight line, essentially, straight as I can make it by hand. And it goes, from H up to B. So this is like our limit. And if you wanted to figure out how much area is under here, by my dashed lines, not my dashed lines, by my forward slashes. Um, so it would just be whatever base times whatever height. That will give you the area. Okay. So we progress a little further. We have another curve here. Now you have essentially a straight line, but it has a slope associated with it. So you have basically an equation that could be represented. Here's a slope intercept form for a line. And basically, whatever the height is along this way is basically equal to the slope. Here's m is the slope, and times x, whatever value of x, as we keep increasing x along this way, and added by some constant c. Okay. This is essentially the intercept, the y-intercept. Well, in this case, this example is just equal to 0. So then it's just going to be the slope times x will give you the value of y anywhere along this curve. And, just generally, you could figure it out. Oh, well, this is just going to be half of what the previous one is, right? It's just half the area. That's one way to look at it. The other way to think about it is just, where are you along the curve is you could actually represent this line with this equation, okay? Okay, another way we can look at coming up with the area under a curve, like, and I see how I drew these little tiny uh, areas. We could come up with an expression to represent the areas, right? If you think about it, what we could do in this case, we could just, if we know like the average height, let's say that we, instead of, saying like from 0 to here, we actually found like the midpoint here on the curve, okay? So we found the midpoint height. And the way we can do that is just to say add y1 and y2. So add this one and this one and multiply it times a half. That would give you the midpoint here. Okay? So that's a good average for this curve at from this point to this point. Okay? So we're going to say the midpoint. Okay. That gives us the height of this. So it's kind of like if we took it and made like a rectangle that was right up to this point, right? And then what we want to do is we want to multiply it times the distance from here to here. So the width. So we're basically creating these little rectangles inside for each of these. And then we're going to add them all up together. So in this case, I would create 1, 2, 3, 4, 5, 6, 7, 7 little rectangles and add those together. And that will give me the total area of this curve. Okay? And that's essentially what we're going to be doing. We use it. So for this is the area of this one, of each little incremental piece. We could do this for any arbitrary function. We could just take, and here's just a quick example. We could take and go through it and just add up these little tiny incremental areas and then come up with a good estimate, or, depending upon how small your little increments are. So if you made this smaller, the distance between here to here smaller, you get a better estimate essentially of your area. Okay, and we'll look at that. We'll actually, there's a specific function in here that we're going to take a look at, but as we go through and write the code, what we'll do is we'll make sure we'll try something like this to show you that it works out pretty well. Okay, to start with, then we'll modify it.